Hello there, Mr. Chan here for Algebra 2. We are about to start a new chapter, 6-3, called Logarithms. Grab your note takers and turn to page 149. Logarithms were created to solve certain types of functions. Quick little brief review of what we've been doing in past years in Algebra 1 and now Algebra 2. We dealt with linear functions, such as x plus 3 equals 5. And to solve for the variable x, you would undo operations and move, the 3 over to the other side. That would be subtract. We also dealt with power functions, x squares, x cubes, whatever. How about x squared equals, say, 9? Well, you would apply the inverse of square, and that would be square root, wouldn't you? Now, when we get to this Algebra 2 chapter, we have things called exponentials. Exponential functions look like this. 2 to the x equals 32, for example. The variable is in the exponent position. It's a lot tougher to guess those answers. In a few moments, when we move to the next page, we will find out that the word logarithm is referring to the inverse function to solve for exponential functions, like square, square root, minus, plus, multiplication, division, so on and so forth. Okay, we have a little word problem to start off with. Don't worry about it too much, the actual lot of vocabulary here to digest here. Earthquakes make seismic waves through the ground. The equation y equals 10 to the x, and there it is, my exponential function, relates the height or amplitude in microns of a seismic wave y and the power or magnitude x of the ground shaping it can cause. So if you look at this table right here, where they filled out most of it except for what the heck's going on with the third row. Now there's a typo here. That should be 5,500. All right, and the question mark is basically asking what magnitude or power in the exponent function will give me 5,500 whenever we bring 10 to that power, okay? So interestingly enough, we have a couple of folks here who approach the problem very differently. Taylor says that 5,500 is halfway between 1,000 and 10,000. That's true. It is halfway. So what he's doing is he is going to look at halfway between 3 and 4, which is 3.5. And that's his answer. He says the magnitude is about 3.5. Is he correct? I don't know. Chen, on the other hand, basically does kind of like a guess and check. He knows that 10 to the third is 1,000, 10 to the fourth is 10,000, is a little too big. So he needs to find a number between 3 and 4. He resorts to decimals. A little too high, a little too low. He's playing a game higher or lower, basically. Too high, too low, and he's just approximating. And he gets to the point where he's very satisfied. When he pushes into his calculator 10 to the 3.74, he gets approximately 5,500. So that's his guess right there. Okay? Very good. Next question. Hey, what is the magnitude of an earthquake with amplitude 100,000? So basically 10 to what power equals 100,000? Now, this is an easy one. 5,500 was not something that was a power of 10, but 100,000 is a power of 10. There are 5 zeros, which kind of tells me from experience, x equals 5. And that'll give you your answer. Yay. Let's critique Taylor and Chen's work. Is each method valid? Now, Taylor's work was based off of finding something halfway. Halfway is linear. We are not dealing with linear functions here, folks. We're dealing with exponential, right? So I'm going to discount or ignore Taylor's work. Chen, on the other hand, plays this game of high and low that I wrote up there. Very good, Chen. And I say he has a better method. In fact, his method is called interpolation. You know, he's checking the high and the low values and see which ones get to his original answer. So he did a great job. Interpolation is like a fancy way of a very methodical way of guessing. All right, let's jump to the next page. I'm going to skip these questions right here. Next page. All right, I need to define what logarithms are. Let's start out with something very straightforward that we learned not too long ago. Here we go. Let's write this in the upper left-hand corner. Let's say we have 2 to the x equals 8. 2 times itself this many times will give you 8. Let's remind ourselves what each part of this particular equation is. The 2 is called the base. The x is called the power. The 8 is the argument. Okay? And when we apply these equations and do math with them, we are doing a form of exponentiation. It's a fancy word. And you definitely see the word exponent, right? Exponentiation is the name of this particular work. Because of the power. Exponent, yeah? Logarithms. It's a fancy word, and it's basically the inverse of exponentiation. Now, earlier, Chen did a method called interpolation. Many, many, many years ago, they came up with a form of interpolation that allowed them to get more and more accurate, you know, multiple decimal places. Nowadays, they're now built into your calculators. Before these fancy calculators, we had something called log tables, short for logarithm tables, and you could look it up for an answer. Like in the first example, 5,500, and basically those numbers are built into the calculators now. You just have to look for the LOG button on your calculator. Okay? Now, get ready. This is not something that's difficult to understand. You just have to understand this is another way of writing the inverse of exponents. Okay? Here we go. Logarithms are log, written this way, base b of x equals y. Okay, so let me say that slowly. Log base b of x equals y. Okay? This is the log form, logarithm form. In the other form, the exponential form, it looks like this. B to the y equals x. They are related to each other. We, for the rest of this lecture, will be converting between one form to the other. This is just an opener. This is just the beginning of these things called logarithms. Let me put down IFF. You guys remember geometry? IFF means if and only if. It goes both ways. Biconditional, yeah? All right. So what this is saying, when you swap x and y and solve for y again, sound familiar? That's finding the inverse. So that's what we have a few seconds ago. This is the inverse of y equals b to the x, because we swap x and y. Okay? All right. So let's try some of those conversions right now between log form and exponential form. So I'll be saying that a few times. You just have to get used to this. It's called log form, and this is called exponential form. And we just convert between the two. All right, here we go. Example 1. Write the inverse of y equals 8 to the x. So when it comes to writing the inverse of functions, the key is swap x and y. Let's do that right now in our problem. When we do that, we get x equals 8 to the y. Oh no! Second step is isolate y. But here's the problem. The y is in the exponent position. Oh no. What do we do? Well, one strategy is to convert it into the other form. Right now, it's an exponential form. Let's convert it to log form. Now, to convert from one to the other, let me show you the technique, okay? Write the words log, and then give yourself some white space and write the word equals, okay? How do we convert from one to the other? All right, here we go. The base is 8. Awesome. Put the base right here as a little number. Okay? The power is y. In log form, the power is on the other side. The answer, or the argument, is x. It goes right here. Ladies and gentlemen, this is the log form of the original problem, y equals 8 to the x. I remember learning this back in high school and trying to think of an easy way to memorize this. So I thought of a boomerang. So think of a boomerang. Boomerangs, when thrown, come back. So see that 8 right there? All right, here's my sad attempt at drawing a boomerang. The 8 is the base being brought to the y power. So think of it, whoa! There's my boomerang being thrown across the equal sign. Oh, eventually that boomerang will fly back. See what I'm doing? 8 to the power of y equals x. So that's a great way to memorize how to write down one version, one form to the other, okay? So think of a boomerang, everybody. Let's try example 2. Let's convert between the two different forms, okay? Okay. What is the log form of 7 to the third equals 343? Oh, yay. Let's write down the word log and equals. Base. Where the heck is the base? Right there. This is log base 7, yeah? Oh, its power is 3. There it is. Power is 3. Think of the boomerang. The boomerang you throw and it goes across the fence to the other side. So that equals 3. And boomerangs come back, don't they? So that is your argument, 343. Now, why are we doing all this? Is because eventually we will be able to use the calculator to punch in and it'll get the answer for us. So there's your boomerang. Whoa, kind of thing. Okay, and there's your answer. We're just converting. We're not solving it, by the way. We're just rewriting it. That's all we're doing. Okay, we're going to go the other way. We have a log form. We just want to convert to exponential form. So earlier we did log form. Great. Okay, remember the parts of the log equation. You start with the base right there. It's a boomerang. It goes to the power of 2. And it comes back to the argument. And that's it. Base is 4, the little guy. Great. Brought to a power of 2. Nice. And that equals to the argument 16. And there it is. Isn't that true? That's true, isn't it? 4 squared is 16. Yay. Okay. Well, I need to bring up something that's going to be important for the next few sections and examples. There are 2 types of logarithms that are built into our calculator. First one's called common logs. Common logarithms. The word common is what we're used to. I mean, if you look at your hands, you see 10 fingers. Our number system, for the most part, is base 10. Common logs are base 10. So sometimes when you see a problem written log x without a missing number, without a number, it's invisible, you assume it's base 10 for invisible numbers in that spot. It is invisible, okay? All right. One other thing that we discovered back when we did compound interest problems in the last section, natural logarithms. We'll explain more of this stuff as we go to the examples, okay? This one is based off of how things grow in nature. It's base E. Now remember, log is log as a button because E is so special, natural logs gets its own button ln on your calculator. So keep an eye on that. Mathematically, you'll see this, ln x. ln x is just a fancy way of saying log base E of x. That's all. It's just log base E, okay? No big deal. This will come into play later on. Let's not worry about the habits of mind. Let's jump to example 3. Okay, now I need to warn you. These problems here are meant to be done without a calculator. And they're meant for you to play around with the bases. You've done this before with exponentials. Here we're going to do with logarithms, okay? Let me explain with example 3a. We have log 3 of 1 over 81 as an expression. That doesn't make any sense. Let's make this into an equation, okay? Let's do that. Let's set it equal to x. Right now it's in log form. At this point, we have no tools, no methods on the calculator that we know of yet, but we can convert to the other form. So let's convert that log to exponential form. That's the key here, okay? All right, here we go. The base, the little guy, is 3. Boomerang is x equals, comes back to 1/81. You've done problems like this before in a previous section. We're just converting it from logs. You guys see the 3 right there and the 81? 81 is breakdownable. These are problems where you want to find the same base. Convert to the same base is a strategy, okay? That 81 is 9 times 9. 9ers are 3s. See what's going on here? Sound familiar? We're just going to rewrite that 81 to 3 to the 4th power, okay? So let's do that. 4 3s, great. Oh, look, it's almost the same base. We just need to shove that 3 to the 4th upstairs. To move it to the opposite side of the fraction, we need to introduce a negative exponent. We're going to force it to go upstairs. Bam, there it is. The bases are the same. Therefore, the exponents are the same now. Okay, makes sense? X equals -4. Interesting, not too bad. So you've done this before. We're just adding on the idea of changing it from logarithms, okay? No big deal. Okay, let's try the next one. Set that equal to x is my suggestion. Let's convert it to the exponential form. The base is 7. Boomerang time. Woo! To the other side. 7 to the x. Great. And the boomerang comes back. Woo! Over the fence. This equals -7. Okay. Well, this is weird. I'm looking at this. Could I ever bring a number to a power and get a negative answer? That's the trick, right? It's impossible. We can never get a negative number. No way. Here, we have no solution. We can never bring a power to a base and get a negative answer. That's impossible. X1 in this row. Let's set this equal to x. This is a little complicated here. The base is 5, the little 5 right there. And let's write it down. 5, boomerang to the other side, x equals 2, boomerang, oh, that whole thing right there, 5 to the 9th power. Great. Oh, that's easy. X equals 9. In fact, wasn't the answer staring at us all this time? You guys see that little 9 right there? This leads us to something really cool I'm going to show you right now. It's like when you guys apply square root, things cancel. Minus plus, 0 pairs out, right? Multiplication, division, the fraction goes away, right? Here we have log base 5 of 5 to the 9th power. Those 5s seem to cancel. In fact, keep this note. If you ever have log base b of b to the x, in a way, those b's cancel each other. This will give you x. Kind of like the log base 5 of 5 to the 9th, you just get a 9. Same goes for exponential. B to the log base b of x. It seems like these cancel right there. And that'll equal x as well. So keep that in mind, yeah? All right. Let's get to the next page. Ooh, some calculator work in our future. Good time to play around with that. Find a scientific or graphing calculator. Oh, round everything to the nearest 10,000. Wonderful, okay. So if you take a look at these, we're going to use calculator work with common and natural logs. Those are two bases. Common is base 10. Natural is base E. Those are built into our calculators. You just have to punch in log of 325. That's base 10, by the way. There's a little 10 right there. All right. So what that means, literally, 10 to the power of something equals 325. That's what that means, okay? Well, let's go ahead and break out our calculator and punch that in calculator. Here we go. So I need to find the log of 321. Let's do it. I think I have to punch this in backwards. 321 log. There it is. 2.5065. Great. Copy that over here. So with the graphing calculator, we punched that in and we got approximately 2.5065 is the answer. Remember what this means. This literally means 10 to that power equals 321. That's what that means, okay? All right. Oh, next one, natural log, which means this is the same as log base E of 1,250. E is 2.718. Remember that from compound interest. Okay, let's punch that into the calculator. Great. Cancel what we got earlier. We're doing natural log of 1215. This calculator, I got to punch it backwards, unfortunately. So ln, boom, 7.025. Very good. Let's copy that down. X and the double, so it really means approximately 7.1025. That was not too bad. Okay. It literally means, quick check here, E to that number, 7.1025, will give you approximately 1,250. Okay. The key is approximately. I should be careful with the equal sign. There we go. And the next one, log 0.17. This is base 10, of course. And we're just trying to find out 10 to what power equals to 0.17. Now think about that. That's going to be a small number, isn't it? Smaller than 1. If it was 1, it'd be 10, right? So that's a good guesstimation there. Let's punch that into the calculator. Here we go. Okay, cancel that. 0.17 log. Ooh, we get negative 0.7696. Let's copy that over here. Negative 0.7696. Yay, that was not that bad. Very good. I want to throw in one more example, folks. Find the natural log of negative 1.87. Think about what this is. This literally means I want you to find the log base E of negative 1.87 equals x. Could you bring e 2.7 to a power and get a negative answer? Ooh. The answer is no. That can never happen, which means for D, the answer is error or no solution. Okay. In order for log x or natural log of x to be defined, what must be true about x? So here's the thing. X, meaning the argument, has to be positive. That's the key. Okay? Has to be greater than 0. All right, number 5. We're actually going to get to solving the equations. It's not as bad as it looks. It's just like, adding, subtracting, multiplying, dividing, square rooting. We're just throwing in logs. Log is a function that helps you solve, interpolate answers based off of data that's been collected and put in as algorithms into your calculator, blah, 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 blah. All right, let's take a look at number 5a. We have logarithms. We want to convert product to exponentials. Let's do that. In this case, the base, oh, what's missing here? The base is a 10. Let's go and convert. 10 to the power of boomerang 2 equals to, boom, the argument, 3x minus 2. Look at that. That is so easy now after converting from log to exponential form. Yay. Well, we know what 10 squared is, and what's 100. Great. And the rest is just undoing operations. Something you've been doing since Algebra 1. Ta-da. Does 3 go to 102 equally? See 3. Oh, yeah, it does. 34. Sweet. Nice. So converting to log, I'm converting from log, which takes a little practice. Oh, we have e to the x plus 2 equals 8. Okay, so what I'm going to teach you right now is a trick to get rid of e. E is the natural base. There's a cool trick. Moments ago on the previous page, I showed you the log of base b of b to the x is equal to x. I'm going to give you the similar identity right here. Right? Here we go. 2 of them. The natural log of e to the x equals x, because these guys are inverses of one another. They are. Here's another one. E to the natural log of x also is equal to x. Those are inverses of one another, like they cancel, like square root. Pluses and minuses. Over here on the left-hand side, I have this e I want to get rid of. Here's something I can do. I can take the natural log of both sides, kind of like adding, subtracting, multiplying, dividing. So I'm going to ln both sides. That's it. If I do it to one side, I got to do it to the other side. Okay? So guess what happens to the ln e? Those go away, leaving with an x plus 2 equals natural log of 8. And just move the 2 to the other side. Please be careful here. 8 is buried inside the function ln. The minus 2 does not affect it. You just leave it alone like that. Let's break out the calculator and see what happens if we take a natural log of 8 and subtract 2. 8 natural log, here's your ln down here. Subtract 2, and I get approximately 0.079. Good enough. Yay. Dun, 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 0.079. Oh, there's thousandth. There it is. So we just picked up a lot of little things there, okay? I'm actually going to skip number 6 this year. And let's jump to the last page. Oh, let's answer this habits of mind really quick. How do logarithms help you solve an equation in which the variable is an exponent? So basically, logarithms, kind of like the boomerang, rearranges the formula for us. So I wrote down last year, relocates the variable, kind of like the last few examples we just did, so it's solvable. That's all. You guys ready for the last page? I'm excited. All right, last page here. Number 5, write each equation in logarithmic form. Right now it's definitely an exponential form. We want to convert that to log form. And to do that, let's identify all the parts again. The 2 is the base. The -6, of course, is the power. And the 1/64 is, of course, the argument. When you convert to a logarithm, write down log and equal sign. The base goes right here, log base 2, and the power is -6 goes to the other side. And it comes back and it equals to the argument 1/64. Yay, there it is. Not too bad, right? Number 6 is next. We have a base E, that's kind of interesting, which means we're going to be doing with ln, natural logs. And we're going to convert everything to log form. Power is 4. And the argument is 54.6. And let's set that up. Log base E equals to the 4th power. Argument is 54.6. Now you can replace that with ln, that's fine too. Actually, that's preferred. There's your answer, yay. Not too bad. All right. Number 7, write each equation in exponential form. We're going the other way. Nice. So in this particular case, log 200 is approximately 2.301. There is a missing base. We're assuming that's a common log right there. And that's base right there is to the power 2.301. And the boomerang comes back and equals 200, and that's all you have to do. Pretty straightforward. So 10 to the power of 2.301 equals to the argument 200. And that's it. Easy peasy. Number 8, similar. We have ln 25. If that bothers you, you can write down log base E of 25 is approximately 3.22. There's your base right there. E, boomerang 3.22. And that comes back. That equals to, of course, 25. And that's it. Not too bad. Yay. Number 9, evaluate each expression. 4, log base 4 of 64 equals to, let's set it equal to x, okay? We're actually creating the actual formula, just like number 7 and 8. We're now going to convert to the other form. Our base, of course, is 4. The power's on the other side. And of course we have the argument. Okay, so 4 to the power of x equals to 64. Yay. Pretty easy? Yeah, it's pretty easy. You got this. Ooh, look at this one. Set that equal to x. We have the bases. Oh, there's an invisible 10 right there. And the power's on the other side, of course. And that equals to my argument, 1/100th. And just put it into your formula. 10 to the x power equals to 1/100th. Oh, wait, I just realized something. They want us to evaluate, not just convert. We have to do a little more work, don't we? Whoops. 64 is break it down because we're trying to solve for x here right now for number 9. Going back to number 9, sorry about that. 64 is 4 times 4 times 4. Some of you might break it down to 2s, and then you realize that 2 to the 6 is the same as 4 to the 3rd. That's fine as well. Oh, there it is. X equals 3 after your bases are the same. Yay. Number 10. Oh, I see that 100. That's 10 times 10, isn't it? Try and keep it real there with the same base. So I have 10 to the x equals to 1 over 10 squared. Let's force the 10 squared upstairs. 10 to the x equals 1. Whoops, my bad. When I force it, it becomes 10 to the negative 2 power. Therefore, my answer is x equals negative 2. Ooh, interesting. Number 11, L and E, those are inverses of one another. They cancel. The answer is 5. No way, that easy. Let me prove it to you. Set it equal to x. The base is e. Here we go. E to the x power equals to e to the 5th power. That whole thing. And there it is. Bases are the same. The exponents must equal to each other. Okay, well, that's it. Thank you very much. Let me know if you have any questions. I'm going to skip number 12 there. Have a good day. Bye-bye.